Okay, so here's how this goes. First of all, welcome, intermediates, to hands-on training. And normally the things that I do in this course take 3 hours. And usually we can't get through them all in 3 hours. So we are going to try to do roughly half of what I normally do. But I want you to have everything. And so if you follow the links on these slides, the first link is to join a group. So you go to that link, and then there should be a blue join button somewhere on that page. You just join. And if it says, like, you don't have permissions to post or whatever, just ignore that. That's fine. You just have to be in the group.
How about you can't view topics?
Doesn't matter. You just have to be in the group. So once you are in that group, in the group for which you cannot post and you cannot view and you can't do anything, you're just in it, that's okay. The next thing is to follow the second link. And the second link is to accept the shared repository. Okay? All right. So now everybody has the shared repository, and you have all the code that we usually teach in this section. And so we're going to try to reproduce this starting from 0 for one example at a time. And that's the hands-on part, is that you guys are supposed to follow me and watch me type code, and you're going to be typing the same thing. And it's all just going to go swimmingly well. But if everything goes sideways, and occasionally it does, we have these scripts in the repository. We can just fall back on those, and that'll be our working examples. Okay? Does anybody still need these links? It worked? Does anybody else have problems getting the shared repository? You should have a EE201 shared repository in your Earth Engine scripts folder after following these 2 links. Please raise your hand if you still need these 2 links to be up. Good. Next thing is to be here at the code editor. And I am proposing that the first example that we do, I was going to do unmixing first. Yeah, let's try unmixing first and see how that goes. Okay? So, spectral unmixing. Ready? Okay. Now, I need to tell you a little bit about the spectral unmixing model first. The linear spectral mixing model assumes that each pixel is not pure. Specifically, it is a mixture of known spectral end members. And what we call spectral end members are just the known spectra for pure land covers. For example, bare land might be a spectrum arranged into this column of the matrix of known end members. Vegetation, the known vegetation spectrum might be in this column, and the known water spectrum might be in this column. These are unknown fractions inside a pixel. This is the observed pixel vector. So for example, the blue band in the observed pixel vector is assumed to be a linear combination of the blue in the bare end member, the blue in the vegetation end member, and the blue in the water end member. So what we have here is a little matrix equation of this form, where S stands for spectra, F stands for fractions, and P stands for pixel. S is known, P is known. We want to solve for F in this equation. Questions about that? Good. Next, go back to Earth Engine. And the first thing that we are going to do is import the Landsat imagery that we're going to use for this exercise. So I'm going to search Landsat 8 TOA, and what you should see is a USGS Landsat 8 TOA ortho-rectified, which is the first result for me. And I am just going to import that, and I'm going to rename it lowercase L8. So everybody should have a lowercase L8 sitting in your imports. And so the next thing is to make a variable which is going to store that the bands that we're going to use, just a list of bands, band names that we're going to use in the unmixing. And that's going to be specifically B2, B3, B4, B5, and B6, and B7. And now we want to get an image. So specifically, I'm going to say var image is going to be equal to the L8 collection. And we're going to cast this at the end here. There's going to be something else that goes in front of this, but let's just fill in the rest first. And dot filter bounds, and I'm going to introduce a bug here, and we'll see if you can be my compiler. So we're going to sort this by cloud cover. That is a variable that USGS sets on all the Landsat imagery. Dot first, and finally select those bands. And that is not needed. That is, and let's see what we get. Print image. What's going to happen? Point is not defined. Fear not. You may see these kind of errors, and that's okay. Point is not defined because we forgot to define our region of interest. So let's just go to a region of interest, which is going to be San Francisco. And here's San Francisco. And generally, what I like to use for this example is SFO. So I'm going to put a point. Let's see. I'm actually going to put a point. So the problem with putting a point near SFO is that there's scene overlap there, and we may or may not get the scene that we want. So let's go to my favorite place. I went to Berkeley, so go Bears. And we are just going to get a point and drop it in Berkeley. So I just searched for Berkeley. I went to Berkeley. I got the teardrop thing on the left of the code editor. I dropped a point there. Click Exit. When you're done with that, now I have a geometry sitting in my imports, and I'm going to rename that to point. Okay? And run it. And we are already having a problem here. And the problem is that first does not know what it is getting. And so when we try to select on the first thing, Earth Engine says, I don't know how to do that. So the solution is to cast this. So specifically, I'm going to put EE.I image, open paren in front of the L8, close paren after first. And run it. And now it works, and this process of making mistakes and correcting them is sort of just the name of the game for writing code in Earth Engine. So hopefully we're going to be able to debug all our errors in real time here. And if we're not able to, then Mike is going to bail me out, right? Sweet. Okay, so there's our image. And we can look at this and inspect it. You can open and close this thing. You guys should, you're all intermediates in here, so all this stuff should be pretty much old hat to you folks at this point. And here we see cloud cover, and it's very not cloudy in the scene, so that's good. That's what we want to use for this example. And at this point, I can add it to the map. So I can say map.addLayer the image. And oh, by the way, if you are stuck and you want to be unstuck, raise your hand at any time, and one of our illustrious TAs will come and unstuck you, or whatever the proper verb is for that process. Okay, so we're going to add the image. We want to specify the bands. The bands should be, we'll just make this a true color thing. Bands is a list, by the way. Can everybody see this in the back there? It's okay? All right. So bands is a list, and true color is just going to be B4, B3, and B2. And the max is going to be approximately the max TOA reflectance for typical Earth surface targets, which might be somewhere around, anybody? What should I use? 0.3, how about? Okay. We're going to use 0.3, and then it's good practice to just name the things that you add to the map. So I'm just going to name it image and run it. And lo and behold, we got an image in the wrong place. See that? So what happens is this point is overlapping the footprint of this image. So we can fiddle with this just by clicking on the point and dragging it around. So I just clicked the point, dragged it over into Arinda here. Now I'm going to click exit and run it again and see if we can get an image to come into the right place. And maybe I'm just going to move this thing around until it behaves the way I want it to, which is moving it back to SFO, which I said not to do. Sorry about that. Exit and run it again. And it is still not cooperating with me. Let's put it in the bay and run it. And there we go. So all I did there was I kept clicking on this point and moving it around like this.
Point doesn't move.
You click the point and it should embolden itself, and then you can drag it around like that. And exit. So here's SFO. If you are stuck, please raise your hand. Everybody should have a relatively cloud-free image displayed in the code editor at this point. And here is the code that you need to do that. It's not very much code here. Okay, you should have the L8 collection, USGS Landsat 8 TOA reflectance orthorectified in your imports, and you should have a variable called point in your imports, which is a single point. And that is it. And I put my point down here in the bay, and that was just fine.
Why didn't it show up before if it's inside of the...
Well, it's inside the footprint of the image, which may or may not have data. See what I mean?
Yeah.
Okay. Have I already lost half the room? I told you we were going to go fast. You guys wanted hands-on. You're getting it. Hands-on. Okay. How many people here have an image displayed in their code editor? Please raise your hand. Okay, so I'm gonna have to move on here, and if you get stuck, please check the spectral unmixing example in the shared repository. Oh, I don't know what that's doing. Okay. So the next thing is we want to choose some polygons that represent pure land covers, and we're going to take the mean pixel values inside those polygons, and we're going to call those mean pixels, where those mean spectra are pure end members. So we want a bare end member, we want a vegetation end member, and we want a water end member. So typically what I do is I go to SFO. So here I just zoomed into SFO. And that's, let me just show you where that is again. Here's the bay, and I'm sort of zooming in right here. There's SFO. Yeah? Here are the terminals. And I am claiming that these terminals represent a bare surface. There is no water and there is no vegetation growing on SFO terminals. So, the first thing is, I am going to click a new layer. So I'm going to hover on my geometry imports, hovering on geometry imports, and I'm going to click new layer. And I am just going to call this, oh, sorry, I want to draw a polygon in there, so click the polygon thing. So new layer, polygon button. Here's the polygon button, that thing right there. And now I'm going to start digitizing a polygon over this terminal. So let's try that. And sorry, I'm hiding the code here. Let me see if I can draw it like this. Here's a point. Here's another point. Here's a point. I'm pretty sure all this is bare. This is bare. And let me just move the map around a bit. And that's bare, and that's bare, and I think that's bare. We'll find out in a second and close it. Okay, now I want to rename the polygon. So this polygon that I just drew is sitting in my imports. It's called geometry. I'm going to rename that bare. Okay, so I just clicked on the name and I renamed it bare. And let me zoom out. So here's what it looks like. I just digitized this polygon over the terminals at SFO. Okay. Now, over here, just to the west of SFO, is this nice forested area. So here's a lake. Can you guys see this stuff? Not too bad. Okay. So here's a lake. Here's some vegetation. I am going to make a new layer and digitize it in the hills here. So I'm going to say new layer, hovering on the geometry imports, new layer. And this is going to be a polygon, so I'm drawing a polygon. And let me just try to click out a rough vegetation polygon here. Something like this maybe. I think that's all vegetation. That is. Yeah, that's vegetation. That is too. And close it. And that's going to have to be close enough. And I'll rename this vegetation. Okay, and one more. So I'm going to zoom out, and here's the bay. This is all water. I'm sure of it. And so I'm going to say, I'm going to hover on the geometry imports, click new layer. And this is going to be out here in the bay, just to the east of SFO, and we don't have to be too fancy about this. There's our water polygon. And I'll rename that water, enter, and exit, and now we are ready. So here is what your code should look like. You should have the L8 collection, a point, which is your region of interest, a bare polygon, a vegetation polygon, and a water polygon sitting in your imports, which you have digitized over pure areas of the respective land covers. Okay? Now, what we want to do is we want to compute the mean pixel values inside here. So, pop quiz. How do we get the mean pixel values inside these polygons? Reduce regions. Yes. All right, so let's say that we're going to call this, let's see, I'm going to call this the bare mean camel case. You guys know what camel case is? Lowercase followed by uppercase, like the humps of a camel. Bare mean camel case. And that's going to be image dot reduce regions. Reduce region. That is. Note that if I misspell it or have a wrong capitalization, it's the text is black, and when I type the correct name, it becomes empurpled. You guys see that? So image.reduce region and open paren, and oh, I forgot the arguments to reduce region. So what am I going to do? Well, we could go to the docs tab and look for reduce region, or I can position the cursor at the opening paren and press Control Space. And you'll note that when I do that, this list of arguments is helpfully filled in for me. And if I put the cursor in the beginning there and I type Control Space again, now you can look at the docs if you want. These are just some helpful coding tips. But I'm noting that the first few arguments here are, and normally, so there are two ways to do this. You can fill in the arguments in order, or you can provide the arguments by name with a little JavaScript literal object. So let's try the latter. So typically what I do is Control Space, I get this list of arguments, I put an opening curly bracket right there, and now we can just start filling them in. And specifically the reducer is going to be an EE.R reducer. The geometry is going to be the bare geometry, and the scale is going to be what? 30. Let's try that, and never mind the rest. Close curly bracket, and now we are ready to go with, oh wait, there's one other thing that I want to do here. We'll do that in a second. So let's just print this bare mean and see what happens. So print is your friend, and this is generally, thank you, be my compiler. And we print, and if you had quick eyes, you noticed that what it was printing is in fact a dictionary. And the dictionary that it prints is a dictionary in which the keys are the band names and the values are the outputs of the reducer for each of those bands. So what we want here is not necessarily a dictionary. What we want is a list. And we just want the spectral data here. I don't care about those names. So I'm just going to type dot values, whoops, values. And that is just going to give us a list of these values in the dictionary. So let's try that. And now you'll see that it's a list, and there are those 6 things, and okay, that looks pretty good. I'm satisfied that this is doing something of value, and so now I'm just going to comment that, and we're done with it. Next is we are going to get the mean values for vegetation. So let's say the veg means, V-E-G capital M means, is equal to the image. So I can just copy all this stuff. I'm going to copy all that. Y'all see that? Copy, paste. Okay? And instead of the bare polygon, I just want the vegetation polygon. Values. And now var water means equals paste and fill in the water. So here is all the new stuff, all this stuff right here, and you can print each one of those to see that there's nothing going horribly wrong. So I can say print the veg means and run. And okay, that's doing something good. Print the water means and run. And now I get two lists and everything works and I'm happy. So I can comment these print statements and we have some data that we can use as our spectral end members. So we just computed 3 spectral end members. Now, what you might want to do is check to see if these are crazy or not. Sorry, was there a question here? Questions? Answers? Good. Okay. What's nice to do is check to see if these values are crazy or not. And one of the ways to do that is by making a chart. So I can say var chart is equal to a UI.C chart dot image dot regions, and what goes in there. First of all, the image, and second of all, an EE dot feature collection, camel case, open paren, open square bracket, because we're going to put a list of features in here, and these are the features that we're going to use. The first one is going to be an EE.feature with the bear geometry, and then just a label, which I'm going to call bear. So this is just instantiating a feature with the geometry that consists of the bear polygon and a single property called label, which is storing the string bear. So curly brackets are a dictionary here. So the second argument to EE feature is a dictionary of properties. But we're not done. We need another feature. And the other feature is going to be the vegetation polygon. And the label is going to be vegetation. But we are not done. We need another feature, and I could probably copy paste here. But I can't think and talk at the same time. So I forgot to do that. And the label, I just noticed a bug in this code as well, is going to be water. Can anybody spot the bug? Thank you. Label. So that was the second argument, is this feature collection. And now I got to specify some more stuff here, which is specifically going to be, let me just do that like this, and comma, and then the next thing is going to be an EE.reducer.mean. Boy. EE.reducer.mean, and the scale, and the label property, which is called label, and then a vector of wavelengths to use for the x-axis coordinates here. And those labels, and you're just going to have to take my word for it, 0.48, and you can search this stuff on the internet. If you search Landsat 8 band wavelengths or something, I'm sure it will be a hit close to the top. 0.65, 0.86, 1.61, and 2.2. And it looks like we still have an error. I'm going to hopefully solve it by closing a paren, but that didn't work. I've got mismatched parentheses in here somehow. There it is. And that's it. So here's the chart. And let me just see if this works, and then we can get people unstuck as necessary and run it. And a chart is coming, and lo and behold, it looks not crazy. So what do I mean by not crazy here? So here's the new code. We're just making a chart of our spectral end members here. We have a bare spectrum, which looks like an approximately linear thing with high reflectance, and that's about right. We have a vegetation spectrum, and here is a nice characteristic vegetation curve with absorption in the green and, absorption, let's see, red, green, blue. A high reflectance in the near infrared. I'm brain dead, sorry. High reflectance in the near infrared, that looks about right. Water, highest reflectance in the short wavelengths, and then down to 0 in the near infrared. So I'm satisfied. These are not crazy spectra to be used in unmixing. And now we can start doing some unmixing here. So is anybody stuck who wants to be unstuck? Okay. So the first thing is I'm gonna make an array. So what I'm doing here is I am assembling the stuff that goes into this equation. Okay, so here are our end members. I'm going to turn those into an array. Specifically, I'm going to say end members equals ee.array.cat, and I'm going to give cat a list of lists, which includes the bare mean, the vegetation mean, the water mean, and I am going to concatenate this along the one axis. And if you took my arrays course, that will not be gibberish to you. And if you did not take my arrays course, that may be gibberish. Arrays in Earth Engine are lists of lists. And we just specified that we have 3 lists, and we are concatenating those along the one axis. What do I mean by that? Can I take this code away, or are people still copying it? Okay. So think of an array as a 0 axis representing rows, a 1 axis representing columns. We have 3 lists of things. The first list we're jamming in with variation along the 0 axis. So we're putting it this way on the 1 axis, then we take another list, put it in like this on the 1 axis, another list, put it in like that. I have a diagram that illustrates that, but people are copying the code, so I can't show you the diagram and explain arrays at the same time. But that's how it works. 0 axis, 1 axis. Slap in an end member this way, slap in another one like that, slap in a third one like that, and you should have a 6x3 array of end members. Okay? And print is your friend. Let's just print this to make sure there's nothing crazy here. Is anybody still copying this? Okay, so vegetation mean. I made a mistake. This is actually, there's a bunch of mistakes here. So this should be veg means, right? Bare means, water means. So just a spelling error here. And run it. And bare means is not defined. What is it? Bare mean. So yeah, apologies for that. I should probably fix this. So I have bare mean, veg means, and water means. And a list of 6 things. So this is actually a 3x6. No, 6x3. Sorry, it is 6x3. Yes? Earth Engine does not support sparse arrays. They must all have the same number of elements. Okay, so is anybody still copying code here? Okay, some folks are still copying, but if there are questions about arrays afterwards, I can try to address those. There are the end members. I want to turn my image into an array image. So I'm going to say lowercase array, capital I image, new variable, var array image, equals image dot to array parentheses dot to array 1. Okay. And now we want to solve that little equation. So let's see how this works here. I'm going to say var unmixed equals ee.image. So I'm going to cast the end members to an image. And I am going to say dot matrix solve array image. Okay. How many people in here have taken my arrays course? How many people in here have not? Okay. I am going to have to explain arrays because all this is probably total crazy gibberish at this point. And if you are still copying code, please instead ask your neighbor for help and copy their code because I am going to go to my presentation. Apologies for that, but I have to explain arrays. Okay, an array in Earth Engine is a list of lists. There are two axes. There's a 0 axis, which roughly corresponds to rows, and there is a 1 axis, which corresponds to columns. There may be more axes, but in general, we are dealing in this example with two-dimensional arrays, and that's all you need to know. Okay, this is a two-dimensional array. It has a 0 axis. It has a 1 axis. I guess I have to present this for it to make any sense at all. We are going to concatenate arrays. There's our 0 axis. There's our 1 axis. I can take a 1D thing, but Earth Engine doesn't know its direction, so I slap it in along the 1 axis. That's the second argument to array.cat. And I can keep doing this, and that's what we just did with those end members. So think of these things as lists of spectral data. So each one of these is an end member, and we just concatenated them along the 1 axis. So here's that 1 argument. Here's that 1 axis. Here are our lists of pixel values. And we can keep doing that. And that's what we did. And we got a two-dimensional array that way. OK. By doing that, we got a 6x3 array. To multiply our image, or to do any kind of matrix algebra on our image, we need to turn the image into an array image. So we need to go from a multiband image to an image in which each pixel stores a one-dimensional vector by calling toArray. And then we need to go from a one-dimensional array image, or an image in which each pixel stores a one-dimensional array, to an image in which each pixel stores a two-dimensional array, specifically a 6x1 matrix. And we do that by calling toArray1. So this is like calling cat along the 1 axis for every pixel inside this image. Okay? So back to our code. Now this should make some kind of sense. Here is the end members array. It's ee.array.cat with those lists concatenated along the 1 axis. So this is giving us a 6x3 array. Here is our multiband image. After calling .toArray, we have an array image in which each pixel stores a length 6 vector. After calling toArray1 on that, we have an image in which each pixel stores a 6x1 matrix. We can now cast the end members to an image. And this is analogous to saying ee.image1, which makes a constant image with ones everywhere. Here we have a constant image in which each pixel stores that matrix of spectral end members. And at this point, we can solve this linear system. So remember, we have end members times the fractions equals the pixel value, and we want to solve that thing for the fractions. So the reason I made the slide look like this is because here's this little equation right here, yeah? And then when I go to the docs and I type, say, matrix solve, you will see solve for x in this little equation. And that is why I put my end members image and my array image into the shape of that little equation, because now it looks exactly like this little equation, and we can operate matrix solve. Okay? So what you get out of here, and we're done with this end members. What you get out of here is a array people. What do you get out of here? Pop quiz. 3x1. You get out a 3x1 array image. And we don't want a 3x1 array image. We want a multi-band image. And the way to do that is sort of the reverse of this process. And the reverse is, we'll make a new variable. I'm going to call this var unmixed image is equal to unmixed dot array project with an argument for the 0 axis. So I'm going to turn my 3x1 fractions image into a length 3, an image in which each pixel stores a length 3 vector. And now I'm going to get rid of the vectors, and by calling array flatten. And the bands that I want are just going to be called, we just have to name the bands now. So I'm going to call these bear, veg, and water. And that should be that. We will find out momentarily by saying map.addLayer let's see, how do I do this? Unmixed image. And we don't have to do anything. Let's see what happens. Okay. It expected a list, and it got a string or something of that nature. What is wrong with this code? Array flatten expects a list of lists. I gave it a list of strings. So all we need to do to fix this, hopefully, is put some extra square brackets on the end here. Okay, so I turned array flatten from a list of strings into a list of lists. There's only one list in here because we have only one dimension on our image. And let's see what happens. So our chart comes and an image comes, and it looks pretty good. I'm going to scroll this up a little bit so we can look at this image while you guys are crazily typing that stuff. Let me turn off all these geometries so we can see what it looks like. And what do you think? Thumbs up, thumbs down, thumbs sideways? Okay, so what happened? When you take a float image and you add it to the map, by default, it displays the first 3 bands as red, green, and blue, and automatically uses a scale that goes from 0 to 1. And because we've unmixed these fractions, we expect all our fractions to be between 0 and 1. And because of the order in which I put them in here, they are coming out bare is red, vegetation is green, and water is blue. And that's why this map looks like a real map. Now, let's check something. I just activated the inspector tab, and I clicked in the water here, and what do we get? That one is actually not as crazy as I was hoping it was. Let me click somewhere else in the water and see if I can get something more crazy. That's a little better. All right, so what do we have here? We have a negative fraction of bare in the water. I was hoping for a greater than 1 fraction somewhere. If you click around, there you go. Now we've got a negative vegetation, and we've got a greater than 1 water fraction. And I don't think those will sum to anywhere near 1, but that's what happens when your assumptions in this model are violated, is you get nonsensical outputs here. Okay? So we can fix this, or at least we can ameliorate the weirdness with this example, which I will do in a second. But first, are there any questions? Are there people who are still stuck who would like to be unstuck? Yeah, we could have bad spectral end members. We could have not enough spectral end members. We could have a nonlinear mixing. You know, lots of assumptions go into this thing, and clearly something has been violated because it's not working. Now, in the interest of time, wait a minute. When does this end? 4:30? 5? 4:30? Oh, man. In the interest of time, I'm going to have to move on. And it looks like we're going to get through one example here. This next one is going to be totally crazy. We'll see if we can get through it, I don't know, in half an hour. But suffice it to say that there is an image.unmix function which gives you the option of constraining the result to be non-negative and to sum to 1. So everything that we just did can be done in 1 line. Wah, wah, sorry. But the point of doing all this is to exercise our reduced regions and our array operations and so on and so forth. So now you guys know how to do it. If you have some fancy thing that you want to do, you know how to do it with these arrays. But there is image.unmix, which will let you do this in 1 line. And that is in your example. Questions before I take all this away and go to the next thing? Okay. Going once, going twice, gone. So, hands on. You guys ready for another one? All right. What's next? Phenology modeling. Here is our phenology model. The blue is observed values. The red is a harmonic function. The black is a linear function, and here we have a constant value. How do you fit that thing in Earth Engine? Let us try. What else do I have here? Oh yeah, that might be useful. Okay, so first things first, we need some data. And so I'm just going to search for, let's see, we're using mod 13 here. So mod 13 A1 is MODIS vegetation indices, so I'll just import that as mod 13. and enter. And then I'm just going to say var c for collection equals mod 13 dot select the EVI band. Okay? So, those of you who have taken my time series course will recall that the function that we want to fit has 4 terms in it: a constant term, a linear term on the time variable, and 2 harmonic terms, a sine and a cosine term. So what we need is a function that can, that can add those variables to every image in the collection. So I'm going to say function add independent variables is going to, let's see, this is a function of an image, and open curly bracket, and now we can start filling this thing in. So first of all, the date is going to be the image.date. The time is going to be the date dot difference, and we'll just start from the, I'm just going to start from the beginning of the modus data record. So I'm going to say e.date, capital D date, and that's going to be 2001-01, approximate start of modus Terra data record. And I want this to be in units of years and fractional years. So that's the time. And what do we have? We have a sine term. So I'm going to say var sine is equal to time dot multiply, and we have to turn this into radians. So 2 times capital M math dot capital Pi pi. This is a client-side JavaScript function, math.pi, or not a function, a static field on this math class, and that's why we can do this two times business, because this is a client-side thing. And then we just take the sine of it. And let me just copy this whole line and paste it here. And that's going to be the cosine, and instead of sine, it's the cosine. And what else do we have? We have an image of independent variables. So var independence equals ee.image.cat. And we're going to just list our variables here. Specifically, it's going to be sine, cosine, time, and a constant. You need to manually add a constant if you're going to use a linear regression reducer in Earth Engine, which is what we're going to do. And I'll just cast that. And now we're going to return the independent dot add bands image, and I'm just going to scale the EVI here, which is scaled in modus data by 10,000. So I have made this example go spectacularly wrong in the past by getting the order of variables wrong here. Specifically, the linear regression reducer expects the independent variables followed by the dependent variables. And if you don't do it that way, crazy things will happen. So independent followed by dependent, I think that's right. We're going to find out in a second. Yeah? Oh, thank you. Be my compiler. Okay. Next is I'm going to make a new variable called regression, which is equal to our collection with that function mapped over it. So map, add independent variables. We're going to find out how wrong all this is in a second. In fact, let's just stop right there for a second and say print regression dot first and see what happens here. Oops. Not exactly what I expected. Well, let's run with this and see what happens. Okay. All right. Let's see. Regression is c.map independent variables. I'm going to take that away, and now we are going to dot reduce this thing with an ee.reducer dot lowercase linear regression. And the argument to the linear regression reducer is the number of independent variables followed by the number of dependent variables. In this case, we have 4 independent variables. The default number of dependent variables is 1, so we just left that out. So there's the reduce part. And now we just want the coefficients. So I'm going to select that band, coefficients. I think I'm missing an F. Does that look right? You guys really have to keep me honest today because it's been a long day. So array project, this is the opposite, going the opposite way. So the coefficients is a 4x1 array image. I'm going to turn that into a length 4 array image by calling array project. And finally, array flatten, and that takes a list of lists, and let's just give it these names of sine, cosine, let's see, slope, and offset. So let's see what happens here just by adding it to the map. Oops. And I am just going to keep coding in the meantime. So the fact that anything is coming here is good news. And it's not throwing an error. So this is kind of a, printing stuff and adding stuff to the map is a good way to check yourself as you go. So if you've made some logical error or other kind of bug is in here, this is a good way to catch it. We may still have other bugs, which we'll probably discover in a second. But for now, that's a good sign that at least we haven't specified the wrong number of arguments or something of that nature. So at this point, what I want to do is I want to display this by using the hue saturation value transform. And here's what I mean by that. We've fitted this harmonic function, and that harmonic function has 1 cycle per year, and that function has a phase and an amplitude. So specifically, you can think of, and this exists in each pixel independently. So you can think of a vector that's going around the unit circle, and the angle of the vector is the phase of that function relative to the start of the year, and the length of the vector is the amplitude of the function. And so we want to make a map with colors that represent the phase, and the amount of color represents the amplitude. And for all of you folks who had to sit through my time series lecture, apologies for that, but this should all sound familiar at this point. So we're gonna use this transformation, hopefully, to make a map that makes sense. So specifically, I'm gonna say sine is the regression dot select sine, and copy. And now this is going to be cosine. Whoops, not cod, cosine. I guess I'm hungry. The slope is going to be equal to regression dot select slope, and the offset is going to be regression dot select offset. Now, I have to go back to my slides for a second here. Who here is still copying? Who else is still copying? Okay, if you are still copying, please look at your neighbor's code for a second here, because I have to go to my slides. So here's our harmonic function. We've got an amplitude, we've got a phase. What I want to do is express that using the hue saturation value model. And specifically, as I mentioned, the phase is like a vector spinning around the circle, and the length of that vector is the amount of color. And in the HSV model, the hue is that phase, the saturation is that amplitude, and value, we're going to use the constant term for that value. So I'm using this model to display these data, and that's the purpose of this next part. So specifically, saturation is going to be equal to the cosine dot hypot the sine. So the length of the vector, the amplitude of the harmonic function. And let's see. There is a magic multiplier, which is 2.5. And that came from fiddling with these values until the colors came out right. The hue is going to be equal to the sine dot atan 2 of the cosine, so the arctangent in 2 dimensions. So getting the angle of that vector based on the sine and the cosine coordinates. And we just have to scale that to between 0 and 1 for that RGB to HSV model, or sorry, HSV to RGB model that we're about to apply. So we have to scale this between minus math.pi to positive math.pi uppercase pi. That's the hue. And the value is equal to the offset dot with a magic multiplier dot multiply 1.5, and the variable that we're going to call seasonality is equal to ee.image.cat with a list of things, which is going to be the hue, saturation, and value, dot HSV2 R, G, B, and that became empurpled, so that's the right spelling and capitalization of that function. And let's see what happens. So I'm just going to add this to the map. And we'll just call this seasonality. Okay, so there's the new code. I am going to zoom out because I'm getting greedy. And I want to see what the whole world looks like in terms of this phenology model. Okay, who is stuck? Who would like to be unstuck? Please raise your hand. Wow, awesome. Is everybody getting a result who wants a result? Okay, so now can I take the code away and we can look at this image and talk about what it means? No? I heard a protest there. So, the colors are the phase of the function. Okay? So the color represents the time of max greenness predicted in each pixel based on that harmonic model. The difference from white, or the amount of color, if you will, indicates the amplitude of that harmonic function. And the difference from black indicates how much vegetation there was in the first place. So the offset of that function. So things without much vegetation at all are black, like, for example, the Sahara, because we set the saturation to be the offset. Yes? No? Maybe so? Is anybody still copying code? Can I go to my slides to try to demystify some of this? Okay. So here's our harmonic function. Here's our constant, which we're calling offset here. Here's our linear term. Here's our harmonic term. This is the phase, so the time of the year relative to January 1st. The amplitude is the amount of change of this function, so areas with a big seasonal cycle will have more color here. The important thing to remember here, and now I'm trying to demystify this last part that I did here, is that here's the model that we want to fit. This is a harmonic model with frequency omega, which is 1 in our case, phase phi, and amplitude A. You can linearize this model by converting this into two terms with only this argument, which have these two betas that we just solved for. And you can recover the amplitude and the phase from the beta 2 and the beta 3 by taking the hypotenuse of the right triangle formed by coefficients beta 2 and beta 3. So remember that, hypotenuse of the right triangle formed by those coefficients. You can also recover the phase by taking the arctangent of the ratio of beta 3 to beta 2. This is just trig identities here. And so hypotenuse, arctangent, and back to the code, and that is where this hypot function is coming in. So recall that this is the coefficient on the cosine term. This is the coefficient on the sine term. We want the hypotenuse of those two things. And that is where the saturation comes from, so the amplitude of the function. Here is the arctangent in 2 dimensions of the sine coefficient and the cosine coefficient. And that is where the phase comes from. and we have to scale that between minus pi and pi. And that's it. Fun, right? Questions? I have 8 minutes left. Should we try to do one more? Oh, yeah. You guys are just gluttons for punishment. Okay, I wish I hadn't deleted that other script because I could actually use the first part of it again. Maybe what we'll do is we'll just start from the one that's in the repository. I'm thinking classification here. And let's just take a look at that thing. So I'm gonna blow all this away unless there are any questions on this. Yes, sir.
Is there any more scientific way of getting the 2.5 and 1.5?
Yeah. So those of you who suffered through my time series course know that those magic numbers are not required. So you can leave them out entirely and, for example, set the saturation to 1. So just around the top of that color cylinder there. And, but, this is cartography, so fiddling with magic numbers in order to make the colors look nice, not necessary, but that's how you do it. Okay, classification. So I'm going to just go to our shared EE201 repository. I'm going to click classification. I'm not sure what's in here. Okay, so this is a stub. Good. So if I run this, we get an error. So we can actually do the first part of this. So all this stuff is exactly what we did in the previous example. I just picked a region of interest. Here's the region of interest. It's a point. Here it is sitting in Berkeley or something like that. I filtered the date to be just 1 year. I sorted by cloud cover, and then I just got the first image. So all that stuff should be quite familiar to you. Now, what this thing is expecting are some feature collections to be sitting in your imports. And specifically, those feature collections are supposed to represent urban points, vegetation points, and water points. So our work now is to collect those points. And here's what we'll do. Specifically, I'm just going to start crazily clicking some points here. So hover on geometry imports, click new layer. So again, here's what I did. Shared repository, EE201, classification, click that, click run. You get an error. Now we're about to solve this error by collecting points. Hover on geometry imports, click new layer. And now, I don't want geometries, I want points. So I'm going to toggle this, click the little teardrop thing here. It says point drawing. That looks good. I'm going to get some urban points. So San Francisco, definitely urban. Urban, urban, urban. Yeah, that's pretty urban. Here's Oakland. Here's Berkeley, Emeryville, or whatever those towns are there. I don't even know. Lake Merritt, Oakland. Maybe that's vegetation. Maybe it's urban. I don't know. We're going to find out soon enough how good my classification is. I'm just clicking points here, just, sort of for fun on urban areas. I think those areas are urban. I got about 22 points, and I'm going to call it good. So click exit. And now in our imports, we've got this multi-point geometry thing sitting there, which is not what we want. We want to configure this as a feature collection. And here's how you do that. You hover on this import and click the little gear icon. See that thing right there? Everybody got the gear icon? Click that, and this little dialog comes, which is going to let you import this as a geometry, or as a feature, or as a feature collection. And we want to import it as a feature collection. And now I can add a property to this thing. So you click Add Property, and specifically I'm going to give it one property called land cover, one word, and the value of 0. And click OK when you're done with that. And we're going to change the name. Thank you very much. This is called urban. So those are urban points. Say OK. Can I take this away? OK. So now we've got an urban feature collection sitting in our imports. I'm going to go back to Geometry Imports, hover on it, click New Layer, and now we are going to get some vegetation. And let's see what kind of a job I do with that. So I'm drawing points in the vegetation. Here is dry grass. I don't know what's going to happen when it sees dry grass. It looks a lot like urban, but we're going to find out what happens. And oh, marin is vegetation. There's marin headlands here. So coastal sage, ecosystem, and go down. There's SFO. Oh, I like these vegetation points a lot too. Near where we got the pure vegetation spectral end member. Remember that stuff? Getting some vegetation. I got 27 points, more than enough. So exit. And now I'm going to do the same thing on this import. So I'm going to click the configure thing. And this is going to be called vegetation, and import it as a feature collection, and add a property called land cover, one word, with a value of 1. OK. Now you should have 2 feature collections sitting in your imports. One are urban points. One is urban points, one is vegetation points, and we still need some water points. So let's collect some of those. Hover on Geometry Imports and click New Layer. And now I'm going to get some points that are water, and that is definitely water. Also the ocean, the deep ocean is water here too. Let's see what else we can get. Water, 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 water. What am I doing? I got 1 minute. Whoa, pressure's on. What are we going to do? 1 minute remaining. There are enough water points, and exit, and configure, and feature collection. Call it water, add property, land cover, value of 2. Thank you. And let us see if this works. Now it's going to try to merge those. Those names look right. So run. And we are trying to do a classification, and there it is. So let me just go through the rest of this in my -0 minutes remaining. First, we use those points to make a training data set. And specifically, that is just the image with the bands that you want selected, dot sample regions. Sample regions is like reduce regions, but it throws out the geometry because you don't need that geometry. And there's the collection that we want. It's just those 3 collections merged together. And the properties that we care about are this land cover property, which is the labels that the classifier is predicting. Always specify a scale. And now we are making a ee.classifier.cart for classification and regression tree, and .trainit. And the training data that we're using are the samples that we just collected. And the class property is that land cover property, which is storing consecutive integers starting at 0. And the input properties are the bands that we want to use. And then on the image, we just select the bands that we want, and we call .classify with the argument of our trained classifier, and display the result, and that is it. Not too bad, right? Typically, when you do this, you're not using these hand-drawn points. You might be, but you might also have a shapefile of points that you collected in the field. Or you might have a fusion table of points that you collected using ODK. So you're taking your Android, GPS-enabled Android device out in the field with an ODK form on it and pushing it to ODK aggregate, which is pushing it to a fusion table, which you are loading into your script, and it has the right labels in it and so forth. So the point here is that we have some known points that represent urban and vegetation and water, and those might come from any number of places. You can get them in by Pand, you can get them in by fusion table, and now you can get them in by shapefile. And we're using those points to train the classifier. And at this point, we can say, well, this classification, I'm not too pleased with this classification. Maybe I want to move one of these points around, so I can click a point and drag it around if you want to change the classification, and that'll result in something different. Better, I don't know, but different. Or you can fiddle with the classifier. So if I decide that cart is not cutting it for me, I can change that to a random forest with 10 trees and see what happens there. And now we get a different, possibly better, actually that result does look a lot better to me. And so you can compare different classifiers and investigate the effects of noise on your training data set and all this kind of stuff. And doing this took us, how long did it take? 8 minutes. Anyway, that's classification. The only thing that we didn't get to, people are going to start coming in, right, Mike? I think we go to 4:30, is that correct? And then it's going to be lightning talks? Who's in charge here? A what? Oh, okay. So actually, oh, okay. So we can keep chatting if you want, or you can take a break. The only thing that we didn't get to in here is the terrain visualization. But that one's, frankly, it's pretty basic. It's making composites with different layers and then using the HSV to RGB model in order to visualize those results. And that is it.